Amazon Alexa or your Microsoft Cortana or something like that, when being asked something so that it can answer properly. Then coming to self-driving cars and parking vehicles, so all of them are programmed automatically so that they can be done without any human intervention. Then the email communications, then web searching, stores and services, and offline experiences. Now we see about that in detail in the upcoming slide. So how artificial intelligence improves social media. So firstly, from Twitter we can see that recommendations, the tweet recommendations to fighting inappropriate or racist content and enhancing the user experience. So we know that the fight between the two actors are being done in Twitter, or spreading of fake news using Twitter. So these are being controlled by using artificial intelligence, so that things like those are being omitted at the time of uploading those. Uploading those tweets. So that is how artificial intelligence works from Twitter. So coming back to Facebook, here deep learning is helping Facebook draw value from larger portion of its unstructured data sets created from almost 2 million people, updating the statuses 2,93,000 times per minute. So here what is it actually is? So even before we are familiarized with AI, around 2012 or 13, when we start uploading our pictures, uh, our faces gets detected once after the picture gets uploaded, and at the time of 2012 or 13 we need to enter the name of the person. But as the time passed around after 2015 or 16, it started recognizing the faces automatically. So at that time, around 8 to 9 years ago, Facebook implemented facial detection, and as time passed by they also implemented facial recognition. So this is how artificial intelligence is being improved in Facebook. Then coming to Instagram, it uses big data and AI to target advertising and fight cyberbullying and delete offensive comments. So to target advertising. So while we are watching all the stories, in between we see ads coming up. The ones which we search, the product which we search, those ads, the ads which are similar to what we have searched, those ads will be popping up in Instagram. So there what happens is the big data plays again. So that the AI is being used so that whatever the product has done, advertisements related to that are being popped up. So it also fights against cyberbullying and deletes offensive comments automatically. Then coming back to chatbots. So chatbots, what it actually does, oh, sorry. Okay, it recognizes words and phrases in order to deliver helpful content to common users. So gone are the days where what we have to do is if we want to ask any help of we can, for example, we have some sort networks like Airtel or Jio, we need to call them up in order to raise any question. But now instead of calling them, we can just open their respective apps so that their chatbot gets open, and all of our doubts and clarifications can be clarified very easily using the chatbot. So what these chatbots actually does is they are pre-programmed with the questions so that whatever the user is about to ask, they are being guessed very easily, so that whatever the query which the user asks, so their answer is being received very easily. So that's how chatbots are being used. Now let us see how artificial intelligence helps you parking your car and driving it. So self-driving cars and parking cars use deep learning, which is nothing but a subset of AI, to recognize the space around the vehicle. So there will be a sensor called LiDAR. So this LiDAR, what it actually does is, it will check for the space whether What happened? Yeah, ma'am, can you hear me, ma'am?
Yes, proceed, Vaibhav.
So it's all right, ma'am?
Yep.
Hello.
Yeah, proceed,
Yes, ma'am.
Vaibhav.
Okay, ma'am. Okay, fine. So the AI power technology that is from NVIDIA, it's already being used in cars made by Toyota, Mercedes, Audi, Volvo, and Tesla, and it is sure to revolutionize how people drive and enable vehicles to drive themselves. So already the vehicles which are made by Tesla, the automated cars, they have hit the roads. Now in the next 5 to 10 years, we can see a lot more automated vehicles being on the road. Okay. Now let us see how AI improves email communication. So the smart replacing Gmail. So here we take Gmail as an example. Now if you want to respond to a mail such as we get an appraisal mail or an appreciation mail. So when we are typing the word thank you, we user, we get a recommendation stating that okay, this user is going to type this message. Now, if I type just yes, then I am working on it will automatically be present so that just by clicking the left arrow mark or just pressing the enter button, the whole message is going to be entered. So that is how smart replies in email are being worked. Now let us see how email filters work. So artificial intelligence is made sure to nearly all email landing in your inbox is authentic or not. So when the mail reaches the inbox, at the time of reaching inbox, it checks whether the mail which is coming is authentic or not. So how it checks whether the mail is being categorized as primary, social, promotions, update forums, or spam is like some keywords are already being programmed via artificial intelligence. So words like so those discounts or sales, so those emails will automatically move on to promotions or any other important mails from schools and offices. So they will be moved on to primary. The mails which comes from social media will move on to the social folder, and any mail which contains spam content will be automatically moved on to the spam folder. So that is how email filters actually work using artificial intelligence. Now let us see how artificial intelligence helps with web searches. So we have an example here with Google predictive search. So now what we do is at the time of 2010, what actually happens is the only after entering one word or a two word, we will be getting the recommendation. Now what happens is at the before I type one word, I will get a recommendation at the time at the place where the search actually happens. So this is being happened due to the algorithm which is programmed by Google. So at the time of 2010, an algorithm called Panda, which was extensively used for Google search. So as time passed by, algorithms like Panda, Hummingbird came, and now we use an algorithm called BERT, B-E-R-T, which is a transformation algorithm. So it uses natural language processing so that all our searches are being predicted as quickly as possible, or even before we type just one word, the whole thing gets appeared so that the time is being saved when searching in Google. And also it uses page rank, which is a ranking algorithm, so that after being searched, so the pages which are mostly visited by the users, they will be appearing on the first page, and the pages which are search list will be appear in the subsequent pages. So that happens using page rank algorithm, and the search happens using BERT algorithm. Okay, so that's what being mentioned here. So Google's search engines evolved over time by studying the linguistics used in searches. So as the study of linguistics takes place, so Google started moving from one algorithm to other, and they are now in BERT algorithm, which we are using now. So AI learns from results and adapts over time to better meet the needs of users. So as users start searching more and more, the natural language processing is also being given with more data, so that the training happens there, so that the search results will be even more predictive than before. So, for example, a search of what are neural networks and how are they related to synapses offers a Google choice of best answer highlighted at the top, which is nothing but this was the particular page opened by many of the users. So that is how Google's algorithm actually works. Now let us see how AI improves your experience at online stores and services. Now, for example, we are when we are searching a product in any other e-commerce website like Amazon or Flipkart. So once after we go to one product, when we are moving down a little bit from that product, that is before the reviews or something. So what it happens is we will be getting a column of products which shows like inspired by your browsing history. Now, for example, I'm searching books which are related to deep learning, which I've just viewed one or two books. So hopefully what happens is the algorithm will recognize that, okay, so this particular user is about to see about products which are related to deep learning books, so that the Amazon's algorithm will suggest me books which are other than what I have searched for. So that is what we displayed here. So below is an example of AI-powered recommendation on Amazon.com. So that is how it's being worked in in e-commerce websites. So it is also personalizing your shopping experience by suggesting new products tailored to your habits. So the next time you are visiting the page, what actually happens is the product recommendation will be shown inspired by your browsing history. So that will be displayed in the home page itself. So that's how AI works in e-commerce website. Now let us see about what machine learning is. So machine learning is nothing but the field of study that gives computers the capability to learn without being explicitly programmed. So what actually being done is, even without being programmed, the computers get the capability of being learned from their experiences, so that as time passes by, their working condition gets better and better. So ML is one of the most exciting technologies that one would ever come across. So it is evident from the name, it gives the computer that makes it more similar to humans. That is nothing but the ability to learn. So machines started learning these things. So machine learning is actively being used today, perhaps in many more places than one would expect. Okay, so this is just a diagram to show that an artificial intelligence as a whole covers topics that are machine learning, deep learning, and neural networks. Now let us see some of the applications of machine learning. So the first one will be image recognition. So I have mentioned earlier, image recognition is used to identify objects, persons, places, digital images, etc. So the most popular use of image recognition and face detection is automatic friend tagging suggestion. So this I have mentioned earlier when we are talking about how AI is being used in social media. So at the time we are uploading an image in Facebook, the faces get automatically recognized and sometimes even gets tagged properly. So even without being tagged by manually, the Facebook will recognize the face and get started tagging. So that is called to be as automatic friend tagging suggestion. So that's what we mentioned here. Then coming back to speech recognition, we get an option called search by voice in Google. It comes under speech recognition and it's a popular application of machine learning. So using natural language processing, we can search any queries by our voice so that we get the result easily. Then comes the traffic prediction. So traffic prediction is explicitly being used in Google Maps. So when we press the traffic one, we can check whether whichever the names which are shown in red, it will show that that particular place has more traffic, and the names which are showing green will tell us those parts are clear and they are free of traffic, free of traffic, and it will show the correct path with the shortest route and will predict the traffic conditions. Now comes the product recommendation. So this also we have talked earlier. So e-commerce websites such as Amazon and also the streaming websites like Netflix and YouTube. So as users start exploring some topics, videos related to those things which we have seen gets recommended every time we open such video sites. So that's how it works. Then coming back to self-driving cars. So self-driving cars, what it will do is it learns the signs on the boards, the signboards which are on the roads, the traffic conditions, the traffic signals, so that according to that, the cars are driven automatically using unsupervised learning method, which will use to train the car models to detect people and the objects. Then coming back to stock market trading, it is widely used there. In the stock market, there is always a risk of ups and downs in shares. So we can use machine learning long short-term neural network for the prediction of stock market trends. So this long short-term memory neural network will have a database of stock market trends of about 50 to 60 years, and it will be learning about how the share market was being used. So according to that, it will predict how it will be, how the shares will, whether it will go up or down in the future. So that can be done using machine learning. Then coming back to medical diagnosis, it is used for diagnosing of diseases. With this, medical technology is growing very fast and able to build 3D models that can predict the exact position of regions of the brain. So, for example, if we can use machine learning in order to detect any type of cancer or any type of brain tumors, just by training a data of brain scans, so that once the the patient's brain scan is being inserted inside the computer, so the machine learning trained model will predict whether the particular patient has brain tumor or not. So that is how medical diagnosis is being done using machine learning. Then these are some of the applications of machine learning in a diagrammatic representation. So we saw about traffic prediction, speech recognition, image recognition, automatic language translation. So coming back to automatic language translation. So if we, so for example, we are opening a page in German. So what Google actually does is, it will show an option in the right side top corner of the page stating that this particular page is in German. So translate, or sometimes the page automatically gets translated to English, and we can just go back to original form. So that is how automatic language translation is done. Then coming to online fraud detection. So online fraud detection happens with using some suspicious activities being detected. Then online fraud detection is being tested. Then comes the virtual personal assistant, then email and spam and their filtering, then self-driving cars and so on. Okay, now we'll see about deep learning. So deep learning is an AI function that mimics the workings of the human brain in processing data for using, detecting objects, recognizing speech, translating languages, and making decisions. So compared to machine learning, deep learning performs well. So that we are using deep learning much in these days. So deep learning AI is able to learn without any human supervision, drawing from the data that is both unstructured or unlabeled. So even without telling the data which we are going to upload, so that can be unstructured or unlabeled. So for example, we upload any images or videos, so they are called to be as unstructured data. So even if we upload such data, so they can draw the data from. Then coming to deep learning is a form of machine learning, can be used to detect fraud detection, money laundering, and any other function. Now let us see how deep learning actually works. So deep learning has evolved in hand with the digital era, which has brought about an explosion of data in all forms and from every region of the world. So this is nothing but it is simply called to be as big data, which is drawn from sources like social media, internet search engines, e-commerce platforms, and online cinemas, and others. So compared to the data which is used 10 years ago, we use it more of them. For example, the data which was used between 2000 and 2010 is being used in just 6 months in 2020 and 21. So that such of amount of data is being uploaded in the internet. So those data can be very much useful for deep learning activities, and it reduces human intervention in places where automation is being done. Now, let us compare between deep learning and machine learning. So, one of the most common AI technologies used for processing big data is being machine learning, which is a self-adaptive algorithm that gets increasingly better analysis and patterns with experience or with newly added data. If a digital payment company wanted to detect the occurrence or potential for fraud in its system, it could employ machine learning tools for this purpose. Now, for example, a person tries to steal the credit card information from a user. Now, all of a sudden, if more amount of more amount of money is being withdrawn from that particular card, or a purchase is being done with more amount, so it will be detected from the bank's database stating that there is some suspicious activity with that particular card, so that the user from his side itself can block that card so that no other problems will occur. So this can be happened using deep learning. So deep learning, being a subset of machine learning, utilizes a hierarchical level of artificial neural networks to carry out the process of machine learning. The artificial neural networks are built like the human brain with neuron nodes connected together like a. So this deep learning is being constructed in a way how human brain actually is. So the neuron is the place where all the data is being stored and it is used from those. While traditional programs build analysis with data in a linear way, the hierarchical function of deep learning systems enables machines to process data with a non-linear approach. So like in traditional programs, what actually does is, it is being programmed properly so that the data which we are giving, the analysis is being done in a linear way. That is done in a singular way. But due to the hierarchical function of deep learning system, it enables the machines to process data with a non-linear approach, so that even if the data is being uploaded, the unstructured data being uploaded, it can easily get trained, and whatever we need, so that can be done very easily. Okay, now we can see about Open Power AI. So Open Power Foundation is an open development alliance which is based on IBM's Power microprocessor. The consortium intends to build advanced server networking, storage, and GPU acceleration technology, which is aimed at delivering more choice, control, and flexibility to developers of next generation hyperscale and cloud data centers. So what Open Power does is, it starts manufacturing power processors which are even more well being used. They have the power even to compete Intel processor, so that they use around 128 threads, which is even more than that being used in Intel processors. So the current version of Open Power power processor is being Open Power 10. So that processor can handle RAM storage of up to 2 terabytes, and it can have storage of around 2 petabytes. So that's how that's the power of the Power 10 microprocessor. And also we do have a YouTube channel called Open Power AI Cloud Virtual University. So in that channel you can find many other videos which are related to high performance computers, artificial intelligence, cloud computing, and so on. So I have just shared some of the fascinating videos on AI. So by just clicking on those links, the PPT will be shared at the end of the session. So just by clicking on those links, you will be redirected to the YouTube channel. The channel name is Open Power AI Cloud Virtual University YouTube channel. You can find around hundreds of videos which are related to HPC, AI, ML, DL, and so on, and also more insights about the power process. So anyone who is interested in power processes can visit our channel so that you can learn more. So these are some of the links. In conclusion, AI makes our lives more efficient every day, and it powers many programs and services that help us to do every day, connecting with friends using an email program or using a right share service. So AI is being played as an integral part in a human life, so that even like chatting with our friends or using right share services is being based upon artificial intelligence. So if you have reservations about use of artificial intelligence, it may be confronting to be knowing that most of us have been using AI on a daily basis for many years. So as I mentioned earlier, that photo tagging was introduced around 2012 or 13. So on those days, we may be unaware of artificial intelligence, but we have been using it for more than a decade. So this is all about this session. I thank ma'am and sir for giving me this opportunity to present this presentation. Thank you, everyone.
Thank you, Vaibhav. Thank you for your detailed presentation about machine learning and deep learning in AI technologies. And talking about open power system, I like to thank Mr. Ganeshan from IBM providing support and help for giving that open power technologies to us. Thank you, Mr. Ganeshan. I'll use this platform to thank to him. And next, I'd like to introduce Mr. Christopher Coleman of our team. He's a scientific consultant and co-founder of Quantum News, who's going to present the next presentation. His talk is about quantum computing and its futures, especially in machine learning. I think it's going to be an interesting session. And Chris, you can start sharing your knowledge and experiences. You can start, Chris.
Okay. Hello, everyone. Thank you for having me. Please just let me know when you can see my screen. I'm about to share now. Can you hear me?
Yes, Chris.
Okay, good. Can you see my screen yet?
No.
5 seconds. And now?
Yes.
Okay. All right. First of all, I'd like to thank Ganesan for inviting me to this talk today. Very happy to be here. I'm going to be talking a little bit about quantum computing, which is an emergent technology. It hasn't been around for too long, so not many people know about how far this field has progressed. And obviously speaking about some of the ways that machine learning and artificial intelligence is combining with quantum computing to help push this technology to the forefront. So as mentioned before, I'm going to be representing Quantum News. This is an emergent startup. It's only been around for about a year, and we focus on the application of quantum computing within the realm of finance. And that's something we specialize on. Just a little bit of background on myself. I have a PhD in experimental quantum physics, specifically quantum engineering. I've worked on various experimental setups used in measurement and control of quantum systems, so developing new qubits, testing out the technologies, and actually setting up the measurement systems that allow us to characterize quantum technology. I also do a lot of work on quantum algorithm, so looking on the software side, how to actually interface these quantum technologies and make them more user-friendly, or try to get them into mainstream. So a quick overview of the talk today. I'm going to be giving a few background information on quantum computing, exactly what quantum computers are, some examples about conventional systems that are already commercially available, a breakdown of the current state of this technology. As I mentioned before, this is quite a new topic and it's very emergent. So it will be a good idea just to take a look at the current state of where these technologies sit and what their computational capabilities are. Then I'm going to take you through some of the real-life applications that quantum computers are already being explored for. An obvious area that is very interesting at the moment is artificial intelligence being applied to quantum systems. So I'm going to be speaking about at least 2 or 3 different applications of machine learning or artificial intelligence within quantum computing, specifically looking at hardware aspects. where we interface quantum technologies with machine learning protocols, but then also looking at quantum artificial intelligence, where we develop quantum algorithms which are merged or combined with machine learning algorithms to enhance either of their capabilities. And then towards the end, I'm going to be speaking a little bit about some of our own activities, specifically joint collaboration with object automation. All right, without any further ado, just a little bit of the background of quantum computers. We all know, I think everybody in this talk at least knows, that conventional or classical computational systems all are based on silicon technologies, which are essentially transistors. Transistors, being classical, work on a binary system, so either on or off, 0 or 1. However, a quantum state, because it is a technology which is developed specifically based on quantum mechanical principles, incorporates a lot of the physics of quantum mechanics into it. So you can have a device which utilizes strange or weird physics like entanglement or superposition. So in other words, instead of just having ones or zeros, as you have in a classical system, you could actually have a superimposed position that is something in between the 1 or 0 state. And this is represented in a block sphere. So it gives us range to a much larger computational space. And this allows us for an information speed up when we start using these technologies. So just to give you an example of some of the technologies that are already out there, this is an example of a very famous 5 qubit quantum processor, which was developed by IBM. These sections over here are the actual superconducting qubits, and these are actually the logic components. These operate in the gigahertz regime, so high frequency electronics, and that's why you have these transmission lines, and these are actually used to pulse or control the qubits. So in a conventional quantum system, you have a lot fewer devices because they're a lot more complex and difficult to control. However, the computational power of these fewer components is actually quite a lot more compared to the classical transistor. So what's really interesting about these systems, you have those qubits, you couple them together, and you can actually develop quantum circuits. And these circuits represent algorithms. And as I mentioned before, because we are dealing with technologies which are based on quantum mechanics, this is a probabilistic theory. So you have to repeat the algorithm several thousands of times, and you get a probability distribution of what your answers are going to be. And this computational space actually gives us solutions to multiple answers to the same question, which is really interesting because it speeds up the kind of computational power that you have in a system. So currently, there are actually several quantum processors already on the market and commercially available. And because this is dealing with quantum mechanics or quantum principles, you can actually build quantum systems on a range of different materials. Remember, quantum mechanics is the physics of the very small. For example, atoms, single photons, electrons, or individual particles that make up the matter around us. So if you can isolate any of these quantum states, you can actually incorporate them into a technology and build a quantum computer. So just to take a look at some of the most famous or well-established systems already, and you'll also notice that these are being explored by a very powerful and big corporations around the world. So these are by no means trivial technologies. Some of the most widely accepted or adopted technologies are the superconducting circuits. That was an example in the previous slide. That's being followed by IBM, Google, new startups like Rigetti, Intel, and a range of smaller companies as well. These are interesting because they are pretty easy to fabricate. I said that because the fabrication processes are the semiconducting industry. So essentially you are creating circuits or chips, and we already know how to do that thanks to the transistor industry that we have. So incorporating or fabricating and scaling up these technologies isn't too difficult with contemporary fabrication facilities. However, because we're dealing with superconductivity, it has a very large footprint. And this is because superconductivity is a very, very low temperature phenomena. So if you build the circuits, you have to cool it down to very low temperatures. And when I say low temperatures, I'm talking about millikelvin regime. Just to give you an idea of that, this is colder than interstellar space, right? Which is about 3 Kelvin. So an order of magnitude colder than what we have in space, you need to cool the systems down to. And that becomes expensive when you try to scale up. However, there are several other technologies which you can actually accommodate at room temperature, and these are specifically the optic systems. Examples of these are linear optics. So you actually have a photonic circuit which is pulsed with lasers, and they have waveguides which direct the laser beam, and you can use the single photons to actually manipulate and conduct your quantum logic experiments. And there are already several corporations investigating these technologies, and this is by no means a primitive technology. INQ last year released a 10 qubit system. What is very interesting about these optical systems is that you're able to couple and combine and entangle the qubits a lot better than what you can do with superconducting circuits or the solid state analogs. So there's definitely a lot of, I would say, advantages or disadvantages between the different technologies. And because this is such an emergent field, a lot of research is actually still being undertaken into benchmarking these different technologies and trying to establish which ones are better for specific or certain tasks. We also have things like quantum dots, solid state spins. Again, these are very interesting because they can be developed or fabricated using conventional semiconducting technologies. However, a lot of work still has to go into scaling these up. But they're pretty established, and you'll also notice that quite large companies are heavily investing in these type of technologies. One thing that I would like to mention is the Majorana qubit, and this is being pursued by Microsoft. This is a pretty interesting or unique technology within the quantum realm because it deals with Majorana fermions, which are fundamentally topologically protected. So if they are successful in developing this type of technology, it's expected that these will be fault tolerant, so your error rate would be a lot or drastically reduced compared to the others, and hence that's why they have started investigating that. However, in terms of developing their own quantum processor, they are a little bit behind the other systems which are already commercially available. So although we have several different quantum platforms commercially available and ready for people to use, the type of problems that we can solve on these systems is still limited. And this is because of the small number of qubits, and also because we are now in a regime known as the NISQ era, which basically means noisy intermediate scale quantum systems. So that means less than 100 qubits, and the qubits themselves are not ideal. In other words, they are noisy. They still are a little bit difficult to control. This noise obviously results in error when you are conducting your experiment or trying to perform some sort of quantum logic. And this reduces how valuable these technologies are. Having said that, we are at a very interesting regime at the moment where the number of qubits that we are now approaching towards 100 in most of the systems is actually falling within the regime where there are very interesting problems that can be solved with few number of qubits. Examples of this are in quantum chemistry, where you can simulate actual molecules and the interaction between atoms, bond lengths, energy levels of these molecules, and also interactions between molecules. Obviously, this is very interesting for the pharmaceutical industry, drug design, etc., etc. There are also several systems being used for optimization problems. Now, as you are probably aware, optimization is used in a range of different industries and sectors. Anywhere that you need to modify or optimize some sort of production line or output. So quantum computers are approaching a point where they are becoming valuable for real life application. And that's only happened within the last 1 to 2 years. So it's a very exciting time in quantum computing. So for those of you that are thinking that quantum computers are still very far away, I mean, if we need thousands qubits, million qubits, you are not correct. Recently, IBM have actually released their roadmap. Within the next 2 years, they plan to have a quantum processor that has over 1,000 qubits. And that's what you're seeing on the screen now. It's one of the largest dilution fridges for this type of system, and it's currently being installed. It's going to have 1,000, I think, and 1,200 qubits that they're going to be able to operate within the system. Now, if you recall from this slide, once you start reaching 1,000 qubits, you're really hitting some very interesting computational resource-intensive tasks, such as factorizing problems that's used in cryptography, database searches, etc. So we really are on the cusp of very exciting technologies, which are probably going to become a lot more mainstream within the next 2 or 3 years. It's not just about the number of qubits you have in a system. It's also about the error rate or the quality of the qubit. That's something I spoke about a little bit earlier. Now, again, as you look at this graph, we're looking at how many qubits you have, right? And we're currently sitting at just under 100. And also the number of gates or the error rate that you have in these systems. And if you take a look at the progression of this technology over the last few years, again, you'll see that we're at a point now where the quantum systems are actually reaching a similar level to what we can do with classical simulations. And that's pretty interesting. This point is known as quantum supremacy, and there are already 2 instances of quantum supremacy having been proven in the real world. One was by Google in 2019. The other one was a Chinese group working on a photon system. So we actually have already burst through the classical threshold. And within the next few years, with the progression of these systems, we're expecting to see a very serious quantum speed up. In other words, quantum computing is likely to take off quite a lot, especially in terms of application. So although we are still dealing with intermediate scale systems, less than 100 qubits, and these are considered somewhat noisy, there are several sectors that have already incorporated or invested in this technology because they have recognized the value of this within the near term. Some examples, as I mentioned, are within chemistry and physics. This is because you can actually use quantum systems to simulate quantum phenomena, which is very important for things like molecular simulations, bond estimates. As I mentioned, this is very important for drug interactions in the pharmaceutical industry. Think about protein folding, supermolecular interactions, peptides, etc. You can use this for physics simulations as well, very exotic things like unified field theories, simulating states of matter, how particles interact, black hole physics, etc., etc. Obviously, very applied sectors as well. We're seeing a large boom in quantum tech in finance. So far, a lot of this research has been directed towards portfolio optimization. And this has been done on quantum annealers as well as gate-based systems, but a range of different companies already offer services for portfolio optimization. We've also seen a lot of work being done in risk analysis, so modifying the models that are used to analyze risk and mitigate risk within the stock exchange, for example, how to help with arbitrage. And this has only been coming into play within the last 2 to 3 years. So we're expecting to see quite a large increase within the finance sector or domain within the next few years. Just to let you know, there are several of the larger banks, global banks, which have already invested in setting up their own quantum computing teams. For example, Barclays, JP Morgan, etc., and a couple of others already have dedicated quantum system technicians, which are working through collaboration with the hardware specialists such as IBM or large corporations to develop their own quantum finance systems. So this is an emergent field, and we think it's going to be very important within the next couple of years. An obvious, very important aspect of quantum computing is in cryptography. So how to quantum mechanically encode information so that it cannot be tapped into or hacked, which is obviously very important in this day and age. Also quantum code breaking. This is because of factorization problems, which quantum computers are expected to be a lot more proficient at solving than classical systems. And obviously, an area that's seeing a huge amount of attention right now is in artificial intelligence, where machine learning or AI is being used to either improve quantum computers, or quantum computing is actually being used to improve the models used in artificial intelligence. So there's a lot of interaction between these two fields, and we're seeing the merger to something known as quantum AI, which is very interesting. So as this is a very active and rapidly emerging technology, there's still a lot of work to be done in improving this and making sure that this is more mainstream. And there are three main areas that we are seeing corporations and research institutes actually investing in. One of them is in algorithm development. So this is on the software side. This are in things like developing the code, software development kits, application programming interfaces that allow people to actually access quantum computers or quantum systems, making it a little bit more user-friendly. There's also a lot of work being done in developing the algorithms which actually run on these systems. Now, because this is a new type of hardware, new type of circuits that are being developed, sometimes they are very unique even amongst each other. A lot of work has to go into how you actually develop or encode the information or map the information onto a quantum system. And this is in the field of quantum algorithm development. So this is obviously huge. And then again, quantum AI obviously overlaps heavily with this. Another sector that is seeing a lot of investment right now is in developing the hardware. So trying to improve the quality of individual qubits, improving the number of qubits, improving how you can connect qubits so that they interact together so that you can have information exchange between these. And all of this also falls under measurement and control protocols. So examples of these are, how do you run the quantum system? How do you deploy the algorithm on this new type of hardware? And how do you extract the information from this hardware? This is obviously a very rapidly developing system. Areas here that we are still seeing a lot of research directed to is fault tolerance. Obviously, as I mentioned before, the error rate is still pretty high in these NISQ error systems. So a lot of work has to go into error correction and also improving the quality of these qubits. All right. So that's quite interesting. The third aspect that we're seeing a lot of or intensive investment being directed towards is human capacity. Because this is such a new technology and very important for the future, a lot of companies don't want to lose out on the potential of quantum. This means that they will have to invest in new skill force, right? Developing the capacity for people to actually understand quantum systems and also run and maintain these systems within the corporation. So quantum education is a very important aspect to the quantum revolution and bringing this technology to the forefront. So, as I mentioned before, there are several limitations with current systems or conventionally NISQ error technologies. And although we've seen huge strides made in this sector, there's still a couple of things that need to be solved. For example, higher quality qubits, understanding the noise and dephasing effects in these systems, fault tolerance, error corrections, more efficient algorithms, etc., etc. One of the biggest questions right now is, how much can artificial intelligence help to solve these problems? And how do we correctly merge these two different technologies? So in the rest of the talk, I'm going to be speaking a little bit about quantum hardware, specifically how we look at measurement and control protocols and how we can interface machine learning systems with these type of systems, right? Qubit characterization, understanding noise and decoherence, the actual physics of these systems, and how machine learning can help us to understand this better and how to mitigate error. I'll also speak a little bit about quantum algorithms today and how we at Quantum News are actually investigating our own quantum algorithms to solve some real-life problems in fintech. So just a little bit of background before I get into the machine learning. What you're seeing over here is a typical readout scheme for a superconducting type qubit system. So basically, as I mentioned before, you will have some sort of quantum device. These are the superconducting or the spin qubit, etc., etc. There are a range of them, as I mentioned. And these need to be cooled down to very low temperatures, for example, within a dilution fridge. What you're seeing on the screen is actually one of the systems that I myself use in South Africa at the research group I'm based at. We have our own quantum program. So these are the kind of equipment that we use there. We cool down the system to about 10 millikelvin, and we use high frequency electronics to control and measure the state of the qubit. Basically, this involves sending down some sort of waveform, which we have control over. The waveform will interact with your quantum device, and it will reflect the waveform back. This reflected waveform actually gets captured by our measurement line, and this tells us information about the actual qubit, what state it's in, after we've been probing it or changing it or entangling it. And this is actually how we perform the quantum logic operations. Now, because we are dealing with a waveform, we know that waves have certain properties. For example, an amplitude and also phase. Now, when we start looking at interference patterns of these waves, we can actually measure the phase and amplitude of these systems, and we can map them as a probability distribution. And this basically tells us the state of the qubit. So what is really interesting about this is that this makes for a very good problem for machine learning. You've got this two-dimensional space, you've got visual information here, and you've got a range of data. And what we try to do with machine learning is try to understand how the phase rate or the state of the qubit changes over time. Because we're dealing with something that's very dynamic like quantum mechanics, it's not that it's a static 1 or 0, just like a like a transistor. So this can actually have a temporal distribution. So a lot of work has actually been done using linear discrimination analysis and various types of machine learning techniques to try to understand exactly what is the time evolution of the state of the qubit. And this helps us to determine the fidelity of the qubit. And the fidelity is just a characteristic metric which tells us how good the measurement outcome or predictable the measurement outcome of this qubit is. And as I mentioned before, these are noisy systems. It helps a lot to know how good or the quality of the qubit is if you actually want to take into account error correction, etc., etc. So that's a very interesting area of machine learning to characterize qubits or quantum systems from measurements. Now, why would this be interesting? Because we're dealing with very novel physical systems, physical phenomena, it's not always easy for us to predict how these quantum states behave. And this is because it's a very new system, and sometimes it's pushing us to the edge of our understanding of fundamental physics. A good example of this is what we're seeing now in Majorana qubits. As I mentioned before, Majorana qubits or technologies is the direction that's being pursued by Microsoft. Now, what's really interesting about these technologies, and what you can see in this schematic over here, they are developed from nanowire structures. So this is a nanowire contacted to superconducting leads, and basically they induce a novel quantum state which gets trapped at this little junction over here. This state is known as the Majorana fermion. The thing about the Majorana fermion is fundamentally it has very interesting properties. However, it is very difficult to measure the system and understand exactly how to control it. So what we can actually do is track the state of this qubit by applying a gate basis and continuously measuring the waveform phase and amplitude, as I mentioned before, and you can actually get some sort of distribution map which tells you the state of the qubit. This again is an obvious area where machine learning would be valuable in determining the transition rate between these levels and giving us a better understanding of how stable these different energy levels or transitions actually are. Now, this is fantastic because it tells us about the fundamentals of the system. So it's a great way in using artificial intelligence or machine learning to understand something more about the physical or the deep physics of these exotic systems. Now, I'm not sure about who is actually keeping up to date with quantum computing, but this is extremely important for this type of technology. Recently, and this is only about 2 weeks ago, Microsoft actually announced that they had to retract a paper on their quantum computing hardware system, this Majorana qubit, because they noted that it was an error in their measurements. This is very sad for the technology because it means that we have a setback. However, if they were properly doing these kind of measurements, machine learning could have probably help them in better control these type of Majorana qubits. So it's very sad to see such a large corporation and big player like Microsoft having to retract or withdraw some of their statements and research. It's a setback for the field. All right, so we've already spoken about how machine learning can be used to characterize qubits, tell us the quality and how good they are. But another very interesting application of machine learning is actually to predict the future outcome of a quantum measurement. And this is by tracking the past measurement within the phase space, as I mentioned before. So again, we can use machine learning to actually feed in data about how we are conducting the measurement. Again, looking at the phase and amplitude of the waveform that gets reflected from the qubit. This again will give us some sort of distribution map. And we can use machine learning to predict what will happen with a specific qubit after you leave it after a certain amount of time, how the state of the qubit will actually evolve after the last measurement. And as you can imagine, this is very important because when you're operating quantum systems, you're exciting them, you perform your logic operations, and then there's some time delay before you do the next one, or some qubits will have to be left out of the circuit before they're brought back in and incorporated into the logic gate. So if their states are changing in between these operations, it can heavily affect the error rate of these systems. So it's a very good idea to try and predict what will happen to these devices or these logic elements, over time. So this is very interesting information and very current. A lot of people directing resources towards this kind of intersection of machine learning and quantum computing. So obviously there's a huge range of different areas where machine learning can be used for data analysis. However, I'd like to speak about one really exciting topic that's only emerged within the last 2 to 3 years, and this is the intersection of visual recognition using neural networks with atomic level qubits. Now, what is very interesting about this type of technology is the qubit itself is a single atom which we can place at a specific point on a single crystal lattice. And that's what you're seeing over here. This first block is just the atomic lattice of the host silicon. And then these blocks over here, or these circles, indicate where phosphorus atoms, right, have been placed specifically for us to develop a quantum system. And as you can see in this image over here, we have up to 9, which are very closely arranged in a specific way to develop a quantum processor. On top of the crystal, you can then have your electrodes, your gates, etc., and these are used to control or excite these individual atoms, which are used as the qubits. Now, what is great about this technology is the way that they actually produce this or insert the individual atoms for the qubits is called scanning tunneling lithography. So basically, this is a very sharp point that has a bias which can pick up and repel single atoms. The interesting thing about this lithography technique is it's also used to image the device simultaneously. And that's why you can actually see what's happening in these type of systems here. Now, what is great about this is you get a very fine detail about the individual atom or the qubit, right, at an atomic level. And that's what you're seeing at the bottom over here. Essentially, because we're dealing with a quantum phenomena, the atom, this is a waveform. So how it is placed within the lattice and the symmetries around that actually dictate the waveform symmetry. And this tells us about the energy levels of the qubit and how to control this. So by using this technique, you can actually map and get a visual representation of your qubit itself. Now, obviously, this makes a great problem for an artificial neural network. This is because you can simulate the type of data, feed it into your neural network, and then use testing data from your actual experiment. And from that, you would be able to predict the configuration of your qubits within the lattice, how they are entangled, the distribution of these, and a lot of information about how to actually control these type of technologies, optimize them as well, characterize them. So this is a fantastic area where we're seeing computer vision and machine learning visual characterization techniques overlapping with characterization of qubits. Very interesting work. So the rest of the talk, I'm going to be focusing a little bit more on the software side. So for example, algorithms, how we develop algorithms, and what we're actually using them for. I'm specifically going to be speaking about some of the activities that we undertake at Quantum News, our startup. So just a little bit of information about who we are. We actually delve or deal in a range of different applications. Our main focus is in applied quantum computing, and this is specifically within the realm of fintech. So we try to provide information or resources for private equity, venture capital, as well as public markets. Our end goal is to develop APIs and SDKs for corporations in order to make quantum computing more readily accessible or bring it into the forefront for various applications. More specifically, we are dealing with the IBM Quantum System. So thankfully to my affiliation at the University of Witwatersrand in South Africa, I actually have access to the IBM online quantum experience. So we can actually access quantum computing systems via the cloud. You don't need access to the actual hardware. And this is an example of a very interesting system that they have, Yorktown Heights. To be a little bit more specific, I'm using the Qiskit within the quantum experience. So anyone interested in getting into quantum computing, I highly suggest looking into IBM system. The Qiskit is very interesting because it's Python based. So it's got its own API, a very easily to learn language, and it also has a great visual representation. So you can actually develop your own quantum algorithm circuits just from visual representation, as well as more from the back end and programming side. And it's one of the easiest ways to get into quantum information sciences. So what we are doing with the IBM Quantum System, one of our main projects at the moment is looking at customer relation management. So as most of you know, and also alluding to the previous talk, very interesting on how big data problems, corporations are actually using large sets of data to analyze behavior of customers or clients, trying to understand better how they react to certain occurrences, etc., etc. So this is a very big problem, very interesting problem that is being solved in a range of different areas, specifically machine learning. One of the most contemporary or well-known applications or types of machine learning protocols used for this are the support vector machines. So basically how to classify clusters of data from clients and how to separate these data sets, how to better understand what are the classification metrics that define these type of systems. Now, classically, these are most easily understood in terms of linear equations, and that's what the classical support vectors originally were looked at. However, obviously, with different types of data, you can have very complex distributions of data, and how to separate them and classify them isn't always very obvious. So what a support vector machine actually does is it maps your data set via a kernel into a higher dimensional space. And in this higher dimensional space, you see that it becomes a little bit more obvious how to separate your different data points. And this allows us to categorize very complex data sets, which are not very obvious. So quantum computing is predicted to be ideal for this type of application because we have a much larger computational space to deal with. It can actually handle a lot more intricate kernels that are used to perform this high dimensional mapping. As you can imagine, quantum systems are already operating in a high dimensional space, so they make an ideal mapping system to access these type of higher dimensional kernels. So what we're actually looking at the moment, and this is in the collaboration with Object Automation, is developing our own API system for looking at or optimizing classical systems via a quantum kernel optimization technique. So basically, we'd be getting in some sort of data from any customer experience, analyzing the data, processing it, and then feeding this into our machine learning protocol. The input data, the training data would then be scrutinized with the quantum algorithm, and we use the quantum algorithm to optimize or modify the kernel that is being used for the mapping, and then we test the system on actual data. The idea behind this is to have a quantum support vector machine, which would be used and hopefully more efficient than the classical versions in categorization and classifying customer data. And as mentioned before, this could be a very useful or very beneficial for organizations that have large customer or client data. Another area that we are exploring is the use of quantum computing for risk analysis. And this is specifically within the finance sector. I think everybody would understand that risk analysis and risk mitigation is very important for finance. Specifically portfolio optimization, for trading, dealing with stocks, etc., etc. At the moment, a lot of this work is being done classically through Monte Carlo simulations. What is very interesting about quantum computing is that with our current systems, we are actually seeing a point where quantum computers are able to outperform Monte Carlo simulations in certain respects. So this is a very rapidly developing field, and it's one of the first instances of quantum computing being used for a quantum speed up over classical systems, specifically in finance. So, for example, again, what we're doing here is looking at a type of algorithm, which is known as a quantum amplitude algorithm. And basically, this involves several qubits which get entangled, a control qubit, and then we use a sampling technique where we rotate individual qubits specifically to some algorithm which we develop, and then we do a measurement test on the different lines, and this gives us a probability distribution which we can actually fit to certain models which tell us about risk, the variance in the risk, etc., etc. And again, these are all very interesting metrics which are used to evaluate real-life systems within finance. So this is another running project which we have. We are specifically looking at the utilization of this type of technique for applications in high-frequency trading. Now, this is very interesting because high-frequency trading is actually a lot more ubiquitous or widely used than day trading. And this is completely algorithmically controlled. So understanding the models which are used to define the risk within HFT is a very lucrative and interesting problem. And if we can optimize these models through a quantum algorithm, that would be a very interesting problem to solve. And that's exactly what we're trying to do at Quantum News. So, having said that, our main application with Quantum News is seeing the overlap between quantum computing, thanks to our access partners, as well as AI, and how these can be used to solve fintech problems. We also look at APIs, developing software languages to allow for easy adoption of these technologies so that corporations can more easily incorporate them into their systems. And we are hoping that we're going to be able to explore this area a lot more in the future. So that's the end of my talk. Thank you very much for your attention. And I hope you learned something from the application of quantum computer and AI, specifically in finance. Thank you.
Thank you, Chris. Thank you for your informative session about quantum computing. Participants, if you have any doubts or questions, I think you can ask. Any questions to Chris? Okay, if you have any questions, I think you can put on the chat window. We can move to the next session. Our next session is about Industry 4.0. I'd like to introduce Mr. Sen, who's going to deliver his insights about Industry 4.0. Mr. Sen, I think you can share the screen.
Yeah, just trying to do that. Let me know when you can see the screen.
Yes, yes.
Is it visible now?
Yeah, yes.
So, good evening, ladies and gentlemen. Welcome to the presentation on Industry 4.0. I'll have a small dive into the perspectives and scopes of Industry 4.0. So, going ahead to today's agenda, we'll cover how Industry 4.0 came into existence, what are the changes, and we'll try to map the changes. We'll look at the key enablers for Industry 4.0 and why Industry 4.0 has to be, embraced in sooner future. And then we have the fields of applications, the challenges, and the use case scenarios. So, well, as you can see, this is the evaluation, and we had seen just maybe most of the participants, including us, most of us have seen mainly Industry 3.0, and we will be seeing 4.0. But the Industry 1.0 was something where we had, mechanization and having the looms, where the machines came into existence, kind of moving on from complete manual labor to taking help of machines. Then in Industry 2.0, we had mass production, assembly line. Industry 3.0, we had automation, computers, and electronics. And Industry 4.0, we had cyber physical systems. So let's try to map out the changes. Industry 1.0, we had the steam machine, the power looms, which I said. Then we had the electricity, which was one of the most important aspects of Industry 2.0 because it helped a lot in having a smooth assembly line. And if many of us can remember, we have the assembly lines from General Motors and Ford, which were the first pioneering assembly lines that we had in terms of the automobile industry, but then we used to also have other assembly lines. Then we have Industry 3.0, where we seen the development of robotics, PLCs, ICTs, and the involvement of electronics. Industry 4.0, going ahead, what do we have, in terms of something new? What is it? So we have augmented reality, we have IoT, we have traceability, we have predictive maintenance, we have artificial vision, we have big data that plays into role, we have simulation, we have 3D printing, cloud computing, CPS, there is cyber physical systems, that is basically a replica of the actual assembly line, in a digital mode. Then we have the role of cyber security and the collaborative aspects. So what are the key enablers of Industry 4.0? So I'll go through one by one in order to make you more aware of where and what differences it makes from Industry 3.0 to 4.0. So we have the Internet of Things now. And most of the applications which we see in the assembly line have some sort of sensing and connecting mechanisms, which are delivering data, gathering data from the system and delivering it or storing it somewhere in the cloud. So this is basically information gathering and delivering from people and systems and vice versa. Then we have additive manufacturing, which also helps a lot in the production area, not just in terms of having prototypes, but also in actual fabrications. Very recently, if you had come across the news of a house being completely built out of cement using additive manufacturing, that is 3D printing, and it's said to be far more strong and durable rather than having the very traditional mode of the building. So the scalability is a question, but then we are working towards it, and hopefully we will achieve it someday. Then we have the role of big data, where data extraction and aggregation of data is a big idea that comes into play. Mr. Vaibhav also spoke about this. We have the application of cloud, where we have the scaling, the ability to scale all of the systems that we are using, the digital technology. So one of them could be quantum computing, which of course allows us to have remote access for computational purposes and not having the hardware, the enormous sized hardware in all places. Then we have the integration platform services, We have artificial intelligence, spoke in details by Mr. Vaibhav. We have robotics. Robotics, we have seen a lot of the rise of robotics in Industry 3.0, but then going forward, these robots were made to be connected, self-sufficient, gathering data through sensors, and having the options to have self-monitoring and self-regulation. So this is where the robotics has evolved. Then we have the augmented and virtual and mixed reality. This helps us, or rather the industrial practitioners, to identify very early in the stages of the production or in the industrial processes what changes could be done, or if done, what are the applications and improvement processes that could be implemented. Then we have analytics. So the data, the big data that we were talking about, that could be used for the analytics purposes. And not just that, we have the data collected from various sensors, as I was saying. So that can be used for the analytics purposes. So these are the major key enablers of Industry 4.0. So what do we have as an outcome when we apply all these enablers in a very systematic and connected format? So we have, a very broad perspective of manufacturing or assembly or the entire industry as a whole, because it's just not production that is being affected. When I talk about industry, there are a lot of, in fact, most of the industries are, getting borderless and getting seamlessly connected. So I'll talk about that in a little while. But before that, we'll see what are the outcomes when we talk about all the key enablers being, integrated. So we have the sharing and analytics platforms. We have the control systems digitally available to us. Then we have the smart sensors and the smart logistics, where all the data from these logistic systems and the sensors can be collected and processed on the data on the cloud for data analytics purposes. Then we have the cloud services, additive manufacturing, cybersecurity, machine-to-machine connectivity. We have robotics. And when we integrate all of these together, then we have the smart lifecycle data. So project lifecycle management, when taken in a systematic manner through these enablers, leads to more sustainable way of having an entire industry. So that leads to smart factories and smart services. So basically, having an entire change of perspective of the manufacturing industry, and we call it the remanufacturing of Industry 4.0. A few highlights or advantages of Industry 4.0 could be productivity. So we have a lot of improvement in the OEE, so overall effective efficiency. And if we look into just the productivity, that would be just narrowing down on one of the aspects, but we have many of them, and I have highlighted just few for, which of course becomes one of the most important parameters for the industry people to take into consideration whether they will go ahead with the Industry 4.0 processes. So productivity, flexibility, speed, and quality. So when I speak about flexibility, we have the options of having control remotely for the entire production process, and not just that, we can have troubleshooting options, and also we can have the option of incorporating any kind of maintenance activities remotely. I'll come to that topic very soon through an example. Then we have the increased speed. So basically, when we have a shutdown these days, it's very common to have people on the floor doing maintenance activities, delivering the data of what activities has to be done, and then coming back to the floor and doing the changes. But now when we have most of the the systems and the sensors connected, the reports and the exact point of origin or exact problem that has happened in the shop floor can be identified very fast, and also the troubleshooting since can be done remotely. So the entire maintenance activity could be completed in a much shorter time, and the production system can keep running without much of an interruption. Then we have improved quality.
I will come in details about how quality can be improved when we are talking about increasing speed. So, few of the manufacturing, conditions which have improved or could be improved that has been observed by adopting Industry 4.0 practices are safety, the working conditions, training and collaboration, environmental protection, so sustainability, and innovative capability or the possibility to incorporate more innovations in our systems. So what are the fields of application? So as I was saying, it's just not limited to the production system. Most of the industries are becoming seamlessly connected or having less of their boundary, which prevents interoperability. So nowadays you can find mechanical engineers working in, let's say, banking. And what will they be doing? Of course, they'll be taking care of certain kind of stuff and monitoring activities. So this kind of activities for the banking is very important, as well as for the hardware and the software. So it's very rampant that we can see people from change of roles of personnel from one industry to another, because industries are becoming more borderless. And just to name a few, like most of the smart healthcare and agricultural applications, then we have the banking and the finance. All these sectors are becoming so interdependent and interoperable. So it's very interesting to see this, that the fields of applications have led to reducing the boundaries between the industry. Of course, any good thing has challenges, and the challenges are of course there to make it more interesting to resolve the to make it more fun and interesting to work on. So the challenges mainly that we face in this kind of scenario and nowadays that we are facing are the integration between IT and OT, where IT is the information technology and OT is operational technology. So there are certain hindrances yet, and we try every day to make certain applications which will try to resolve it on a larger scale. So it's not just unit applications, but bulk applications which get resolved at once, and that's how the integration between IT and OT is being resolved. Then we have the data compliance questions. So which data goes to where and to whom, and the level of access, etc. about data. These questions become important. Then we have the risk. Then we have the challenge of managing risk and lowering the cost. So that's important because we did not have any idea about the pandemic that has, or we are yet in this phase. So how do we tackle or come out of economic slump? That's where Industry 4.0 is trying to act forward in order to not have impact from these kind of setbacks. And then we have the dealing of complexity of connected supply chain. So mostly making the scenarios more boundaryless, or let's say the industry is more boundaryless and then more connected. That's another challenge, and of course it's being worked on. Then we have the better understanding of IT and OT, as I said. And of course, a very important factor that the human challenge, the talent, the future of work, the employment. We talk in these scenarios, or in the present scenario, we talk very little about how people are going to work. What are the talents that has to be nurtured more? What kind of employments will be available? Then there are also doubts whether robots will take away all our jobs, and as such, will we have anything to do or not? So these kind of things are also being tackled, and since the technologies we see that they are evolving at a much faster rate than the talent, this question is a big question and has to be tackled in a very smooth manner in order to not have some gap between what we have and what we want to achieve. Okay, let's come to some use case scenarios. I think that will make the the explanation of Industry 4.0 interesting for the audience. So the first one, design and prototyping applications. So if we are looking at certain aspects, let's say designing, people might question, didn't we have digital incorporations while designing and prototyping? My answer would be yes, we did. But then what we did not have could be the application of augmented reality. So whatever was created digitally was fine-tuned and then made prototypes and then gone for production. But now what happens is we have augmented reality to actually touch, feel, and have a sense of what the actual prototype even would look like. So that's more interesting because every prototype needs a lot of investment of time, of resources. So these can be reduced and actually are being reduced by certain industries, and they are trying to apply more of augmented and visual realities and mixed realities in order to achieve it. Then we have the remote shop floor monitoring. In fact, we have shop floor, not just shop floors, but we have mines monitoring from from remote. So that's one of the most important applications, because at times the maintenance operator might not have the feasibility, or let's say the accessibility at a faster rate to the troubleshooting or to the access to the machines which has to be troubleshooted. So if that can be accessed remotely and can be worked upon and troubleshooted, nothing better than that, right? So that's how we talk about, that's how we can talk about the application of remote shop floor monitoring. Then we have quality check and application of machine learning. So in this picture, you can see robots working. Nothing new, because we have robots working even in the industries that we have currently. So, but what is new then, you would ask me, and I would say, there are sensors, there are monitoring machines, monitoring devices within these robots nowadays, which continuously collect data, not just during the production, but post-production, in order to monitor what has been requested to produce, what was produced, and what were the gaps between the production request and the produced object. So after that has been done, it can be analyzed after a lot of applications that, okay, so we have produced, let's say, a ball bearing, and after a production of, let's say, 10,000 units, we have a factoring ratio of, let's say, 2% of failures, and that gap could be achieved, or let's say reduced through maintenance activities. So this is where the application comes in, where we have less of rejection units at the end of production. So if I say, well, Industry 4.0, very great. Do we have anything for the students? And how do students get hands-on into it? Then I would say yes. And from object automation, we have Industry 4.0 Center of Excellences, where we enable students for the factory of the future, and make them ready for the Industry 4.0 arena. So it's like creating centers of research and development in collaboration with industry players. And this could also serve as a research centers for masters, graduate students and PhD students. The most of the topics that are covered in this kind of center of excellences are Industry 4.0 and IoT, cyber physical systems. Then we have the big data analytics and smart factory and smart products, what they are and what how they are manufactured, and what roles they play in the life cycle management. Then we have additive manufacturing, and we have computational vision. This is one niche area where the application is not just limited to production, but it has applications in a lot more areas, and that's what we try to cover. So what we create is, through prototypes, we try to emulate Industry 4.0 scenario, and we create the research and development arena for professors and PhD scholars, and make students ready for Industry 4.0, and also industry ready, and get them more ready for the industry to be absorbed into. So there are a lot of advantages, not just for the students, but also for the professors. The students can utilize this as a hands-on training opportunity, can have a research and development activities, can have final year project theses, serve as also use this as a platform for startup hubs. And for professors, we can have a lot of broad applications like research scholar guidance and publications of papers, and broaden the scope for research activities for projects for the industry. So thank you for this for reviewing this Industry 4.0 scenario along with me. I hope you enjoyed it, and I would like to open the floor for any questions that you have.
Sen? Participants, any questions for Sen?
Any questions here? Yeah? Object automation. Right. It's in collaboration with IBM. Yes. So the Center of Excellence is in collaboration with IBM, and we are partnering up. Yes, of course. We look into it in different perspectives. So we just not stick to one kind of approach. We have different way in which we can collaborate. Any more questions?
So any questions from the participant sides? Okay. Okay, I think we don't have any more questions from the participant sides. Okay, thank you. Thank you all for making this session a very successful one. Participants, if you have questions, please send the questions on your email, or you can put it on the chat box now. Sen, I think we have some questions on the chat box.
Yeah, I'm trying to answer them.
Yeah.
So how the image annotation is helpful in ML and AI? Very good question, sir. So since we have okay, can I answer this question type through an example? Maybe that would make it more fruitful for you to understand. Let's say, so when we have images, for example, which I was talking about just a while back, that post-production, let's say we have an image of an object that was produced, and that was being recorded, and later on this is just one piece of image, let's say, and then we have so many other production batches coming in. So when we have data from image data from all these production batches, and they are being stored on cloud, later on when we have any kind of issues from or complaints from the market, we can have a referral to these data sets to understand which batch at what moment went, had a problem or went wrong. And that traceability becomes a big help in this aspect. So it just doesn't end there, because it's just not about traceability. It's also about identifying what problems happened. So we can understand which machine went wrong, what were the defects that could have went wrong in that point of time and did not occur later. And that could be, implemented as a predictive maintenance for the later, improvements, to not have recurring problems as such. So this is how, image annotation is, helpful in training for ML and AI. This is one aspect. And maybe this answers your question, does it?
Actually, we have good career in this image annotation with ML and AI.
Sorry, it's going a bit.
Actually, we have good career in this image annotation with MI and AL, ML and AI. How is the career with image annotation?
Yes, you have a good career scope in the image annotation.
Okay, yeah.
Yeah, that is my question.
And Sen, you have another question. What is the difference between Industry 3.0 and 4.0?
Okay, so this question is from Mohammed Imran.
Yeah.
So, yeah, Mohammed. So basically, I'll come back to your question and I'll say that we had robotics, we had the PCTs and IoTs, but we did not have PCTs and ICTs, but we did not have IoT, we did not have cloud applications. In order to have remote access, remote controls, we did not have the application of data analytics in order to have better improvement facilities. So what we had was just the implementation of the technologies like, the robotics and the PCT into the manufacturing domain mostly, in order to, facilitate the life of the, let's say, the production people. But then in order to enhance further the production process itself, the application of cloud and IoT plays a big role. And then we have these applications in order to also make the entire system more borderless between industries. So when we were talking about Industry 4.0, 3.0, we were limited to, production as production. But now when we talk about production, we also, although smart or Industry 4.0 is not completely, active in all the domains, we also talk about smart logistics. We talk about connective, products, and that's how a product development team works. So in order to have the entire data from all these, the players of the life cycle of the product, so this helps in order to improve the product for the future production system. So, or the processes. So that's what is the big difference between 3.0 and 4.0. And what plays a major role in this is the development and the connectivity of ICT and, or let's say the IoT and, and big data. And there are other key enablers that we also have talked about. So these are what plays a key role in the differentiating between both these. Great. And there's another question from what about HMI example. So if I talk about HMI and an example, maybe I would like to give another, I would take this up separately because I would like to give a detailed explanation with an example to you. So if possible, please mention your email ID or write to Object Automation separately. Yeah, that's great. I'll get back to you on this.
Any more questions?
Hello, Sen.
Hi.
Yeah, I've got one question. So,
yeah, sure.
Industry 4.0 is really interesting because we're seeing so many new types of technologies,
Right.
being combined and coming to the forefront. And,
Right.
you guys are involved with interfacing basically a lot of aspects of this together. I just want to know, how do you keep at the forefront of such a rapidly developing field? I mean, there's so much going on, so many new technologies, so many new players in this field. How do you keep a finger on the pulse and you know what's current and what's going to be big?
Yeah, a very good question. So all the participants who are offline present, I'll just repeat your question, Chris. So Chris had asked, Industry 4.0 is very rapidly developing, and he wants to understand how do we understand what are the major changes happening day to day, and what are the most important aspects that could be not tapped into to have the best output. Am I right, Chris?
Correct.
All right. So this is a very interesting question because every day we have sort of 5 to 10 publications if we consider the entire domain of Industry 4.0, and that is to be like, let's say, in a very minimal number that I have spoken. That could be in a day much more than that, and the research is completely going considering that Industry 4.0 will not be enclosed or just get inboxed within just a very small area. Because I'll tell you, Chris, what happens is when we have a lot of factors coming into play, like the 17 goals of of the entire sustainable model. When these come into play, we just have to consider the entire industry as a whole, not just the production systems, but we also have to consider all the parameters of all, or let's say most of the developing industry factors, the technologies. So when we are talking about such a big scenario, your question becomes very important because we have to have a tap on or a track on what and where we are going, we are headed. That's where the role of let's say a little while ago I was talking about what we talked very less about, where the employment is going to be, where are we headed towards in terms of work, what do we have in terms of the type of activities that we will be doing when this entire Industry 4.0 is developed. And it has been realized that Industry 4.0 is not a defined scope that we have, because for the ever evolving technology, for example, when quantum comes into play, we will not have simple computing for data analytics. We will, if quantum gets a big role in the sooner or the very near future. So at that point of time, we will have much more implementations and much more evolving interesting facts from other technologies. And it might so happen that today that we are talking about ML so strongly might not be the most important or the most active participant. It could be taken up by something else, by supercomputing or automated supercomputing, etc. Because there are a few talks, if you have read about it, that there are a few talks about auto computing. So we will not be even doing the computational activity. So we will just create supercomputers with the powers and the prowess to have all these technologies developed inside, and the entire process will be done by themselves. So it's very interesting question, and it never ends when we talk about where the scope or the boundary is limited to. So Chris, this is an ever evolving sphere. We cannot completely keep a track of it. All we can do is keep a pace, or capture the maximum out of what exists of the current technologies in this sphere. Was that okay, Chris, for now?
Yeah, very good explanation. This is such an interesting field because so much is happening. The reason why I asked that question is and I guess this could be a follow-up question, what are the most exciting areas that you are seeing right now, and where do you think are the most exciting developments going to be leading in the near future? I know for myself in quantum computing, we're, like I mentioned in the talk, we're at the cusp of next generation computers and quantum supremacy, but we're seeing large gains being made in a range of other 4.0 industries. What do you think is the most interesting thing happening right now, and what should we be keeping our eye on?
Right now, I think we should keep our eye mostly on machine learning, and we should be developing more the sphere of connectivity and remote access to just not supercomputing, but also cloud. Because the more of cloud space we have, the more of bandwidth we have for data analysis. So I think these 3 or 4 important factors are the ones which we really have to look into when you are talking about maximizing the scope of quantum computing. Let's say that I'll maybe prioritize from scale. So if we look at machine learning, it could be rated as 8 or 9 out of 10. And then we have cloud computing and remote access could be 6 or 7. And that's where we could have a balance between how much we can achieve with these technologies and these evolving technologies right now.
Great, thank you.
You're welcome, Chris.
Thank you, Chris. Thank you for your question. Thank you, Sen. Any more questions, participants?
No, ma'am.
Okay, thank you, participants. We have planned our next session on April 17th. Okay. So
Okay, ma'am.
all the heading and the timings will be shortly announced. So we'll
Okay.
meet on April 17th. Thank you.
Bye, ma'am.
Thank you, ma'am. Bye, ma'am.
Bye, ma'am. Meeting like this. Abhishek. ఇది హెచ్ లో ఉంది కదరా
Vardhan.